starts from chapter 3, which is from chapter 6 of the Shigley textbook. The topic of this chapter is about fatigue failure under variable loading or under dynamic loads. Earlier I have uploaded two videos on the online classroom. You can refer to these two videos to understand what is dynamic load and what is the effect of dynamic load on different parts. But in brief, I would say that dynamic load, which variable during the time between the maximum and minimum value, may affect or it may fail a mechanical part due to the phenomena called fatigue. Fatigue failure normally includes three stages. At the first stage, we will see an initiation of a micro crack. When micro crack starts at a location, for example at A, and then it will be progressed to in terms of macro crack, and then it when the the dynamic loads repeatedly uh, goes through maximum and minimum, this micro crack will propagate and will be expand through the part, and you can find the trace of this propagation on by traces like beach mark, like the trace of water on the sands of the beach. That's why we call that beach mark. And when the remaining material cannot take the load anymore, the static load or the constant when the remaining material cannot carry the maximum load, it will break suddenly. That means this location, this part C, is the sudden failure of the material, and we show that by which is a stage 3. So normally when you look at to the fraction or to the cross section of the fraction, and if you face with this pattern, you may judge that the part has been failed under fatigue failure. Fatigue failure uh, is more serious for a cases with or for a part which has a notch or which is not integrated. It doesn't has integrated or uniform structure. For example, as you can see here, we have a shaft with a key seat. As you can see, the micro crack has been started at the location of key seat, exactly at the bottom of the key seat and at the deep right at the fillet of the bottom of the key seat. The micro crack has been started, and then it will be propagate through the stage 2, and then it will suddenly fail at stage 3. Okay, to understand the length, to determine the life of a part under a dynamic load, normally we will make a test. I believe that you have seen this test in our lab at the material lab, right? We have some fatigue test machines. Also, it is demonstrated in the first in one of the video I uploaded earlier in this classroom. We have two different type of tests, but one of the tests is to use a sample or a specimen like this with this specific geometry. Then we will load it by a static load. Okay, we will load it at here at the top of the surface, and it will be start to rotate. Okay, so when it start to rotate, I would demonstrate it by find the pen here. Okay, never mind. I we we have this shaft. Okay, let's say this is over a specimen. I will upload. I will load it by force F at the center, and if I draw the cross section and I choose a point, let me choose another color at the top. Okay, and I start to rotate the shaft. First of all, because of presence of this load, the shaft tends to bend this way. Correct. At the top of the surface, we have tension. We show that by sigma negative. And at the bottom, we have at the top we have compression. We show that by negative. At the bottom, we have tension that we show by positive. Okay, so this point at the top of this shaft, if I draw a graph, the horizontal line is T, right? And the vertical axis is stress. At the beginning, the shaft before rotation starts, this point A is under compression, and the value is negative maximum bending moment, but compression. When the shaft starts to rotate, okay, let me say at time equal to 0, when the shaft starts to rotate, this point will move to here. Maybe I would say that it is at the time equal to first second. Okay, this is just an example. At this point, because the point will be located at the neutral surface, neutral neutral axis of the cross section, so it becomes 0. Here the bending stress is 0. At the third second, the point will move at down. Maybe I call it t equal to 2, 2. And then that means the point will be located at the bottom of the shaft, which we have tension or positive x. So it will come here, which is positive or maximum stress in, let's say, t equal to 3 seconds. Again, the point will move to middle, which is located at the center. So maximum become the bending stress becomes 0 again, and then it will move to its initial location. That means again become negative. So by continuing the rotation, when the rotation continues, this pattern will be repeat. In this case, because the geometry of the shaft is symmetric, is completely circular, the value of f is constant. Okay, f is constant, c. That's why the absolute value of the sigma max or positive sigma max is equal to absolute value of the sigma mean. That means here I would say that this is sigma mean. This negative sigma max is equal to, okay, this negative sigma max is equal to sigma mean. I mean the minimum value of the stress by considering the sign. So this maximum is equal. This maximum equals to minimum. Because of this reason, because the minimum part is equal to maximum part, we call this stress as completely reverse. You can call it complete reverse stress or complete reverse loading. Okay. Okay. So to find the life of a material when we want to find a life of a specific material like aluminum, like cast iron, like steel alloy, we have to make a specimen or a sample similar to this with this geometry, and then we will apply this constant load at the center, right, F, and it will be a start to rotate. The number of rotation before this part fails will be considered as the life of this specific material, or we will call that fatigue life of this material. If we apply different load, for example, at one time I will do the test by using 1 Newton. In second time I will repeat this test by 10 Newton. Okay. In another time I will repeat the test by, I don't know, 100 Newton. Definitely when I increase the load, the stress on the material also will increase, right? This is something normal. When I increase the load, the stress also will increase. If I, okay, let's say one time I will use this load, okay, and I will get life equal to 10 number of cycles. Another time I will use this load and I will find life equal to 1000 cycles. In another time maybe I use this load and I find 1 million cycles. So definitely when you are decreasing the load you applied here, if you decrease the load that you applied here, you will get longer life. It's something logic, right? And when I draw a graph which cross these points, you can see that after a specific load or after a specific stress, it doesn't matter what load you apply, the life of the material will be infinite. For example, in this graph, if the stress become less than 50 kpsi, if the load that you apply on the specimen result to a stress less than 50 kpsi, the load would never fail anymore due to the fatigue. It continues to rotate infinitely. it will never fail by fatigue. So basically, when you find a life more than 10 power 6 cycle or 1 million cycle, you would say that the life of this part is infinite. Sorry, I cannot write by this software. Anyway, but for some other materials, for steel alloys is very usual to find such graph with infinite life. But for some other materials, it doesn't matter how much you reduce the load or reduce the stress, always there is a cycle or always there is a life in which the material will fail due to the fatigue. That means the graph of Sn, we call this graph Sn graph. Or this graph, would be never become a horizontal line. Always it is decreasing. So for this group of material like roads, aluminium, like the cast iron, we don't have this infinite life. So for this group of material, as long as we satisfy this life, then it should be satisfactory. If we satisfy this life, it should be satisfactory. The minimum strength, this minimum strength in which failure or fatigue failure never happen anymore, we call that this value endurance strength. Okay, this specific value in which the Sn graph become horizontal line, we call that endurance strength. We show by Se. And this endurance strength for a specific material, as I told you, will be specified by tests under laboratory condition. Okay, scientists, they have done, let me find this graph. Scientists, they have done this test for different materials with different tensile strengths. Okay, they have repeated this test by using many materials which they have different tensile strength. Okay, they found out the endurance strength for this material. For example, maybe this is for mm, with for a steel alloy with high carbon, and another one with medium carbon, and another one with low carbon. Okay, normally with reducing the percentage of carbon, the strength of material increase. So they try this test for different material and they record down the endurance strength. They found out that, okay, each point here represent for one test. Okay, each point represent one test. They found out that normally this endurance strength value falls between 0.4 and 0.6 or 40% and 60% of ultimate strength of the material. It falls always between 40% of ultimate strength to 60%. So we can conclude that endurance strength of materials, those with infinite life, we are not or talking cast about iron. The endurance strength of material with infinite life is normally 50% of ultimate strength of that particular material with a good approximation. So this is kind of approximating the endurance strength of a specific material. I would use a prime symbol here, Se prime, to show that this is the endurance strength of the specimen that we use in the lab. Okay, we are talking about a length that we are talking about the life of a specimen with this geometry and under the lab conditions such as the temperature, because the actual parameters, the actual part that you use for a application, for example, you want to find the endurance strength of a shaft which is working in a gearbox. That shaft geometry definitely is different with this shaft or with this sample. The temperature of the operation is different, and the surface quality of the shaft, that particular shaft definitely is different with this sample, because normally for lab sample it has very smooth surface finish. So we will use this prime symbol at the top to shows that this is endurance strength of the material under lab condition. And then if you want to find the endurance strength of a part, for example like a shaft under working condition, then you have to multiply this endurance strength into marine factors such as Ka, which is surface factor, Kb, size factor, and others, and etc. Okay, here I'm not going to explain how to draw these graphs, and because we don't have enough time to explain these graphs, I just intend to explain about some important parts of this chapter. So basically, when ultimate strength of the material is below than 1400 megapascal, we can use this equation to estimate the endurance strength. And for a material that ultimate strength is greater than 1400 megapascal, the endurance strength is for 700 megapascal. Okay. Now, to check whether that a sample is going to fail under fatigue or no, first we have to find safety factor of a sample. Let me find the equation for you. If safety factor of, or let me say, if the fatigue safety factor of the part is less than 1, then we would say it will fail under fatigue failure. So I will subscribe F for N. That does this means they are talking about the fatigue safety factor. How to find the fatigue safety factor? We have to write here the Se prime. Okay, I'm talking about the standard specimen over sigma max. Okay. if sigma max is greater than SE prime, then NF will be less than 1. And then you can conclude that the part will fail under fatigue failure. If NF become greater than 1, then you will conclude that the cycle or the life of the length, the life of the part will be more than, or let me see, will be more than 10 power 6 or 1 million cycle. So this is called finite life, finite life, and this is infinite life. In finite life, n, or the number of cycle of the part, is less than 10 power 6. So now the procedure is like this. First, you have to find the endurance strength of a material. You have to find the maximum stress, and then you need to check whether it has finite life or infinite life. This is the first thing that you need to do to find fatigue safety factor of the part. Now let's say that I have found the fatigue safety factor and become less than 1. I want to find out if the life is not greater 1 million cycle, then how much is the number of life? How much is the number of cycle? This is a question for me. How many number of cycle is the life of this part? Or in maintenance, for example, for aircraft parts, each part has a life, and we know that after how many hours working or cycle, the part should be changed to avoid any failure or any disaster. So to answer this question, first we have to find two parameters, parameter A and parameter B. Equation of parameter A, SUT is ultimate strength, SE is the endurance strength, and what is F? To find F, which is fatigue strength fraction, you have to refer to figure 618. This fatigue strength fraction is a function of ultimate strength. The metric version of this graph is provided in your lecture note, and it will be provided in the appendix of exam. For example, if you have a material with ultimate strength of 100 kpsi, then F, or the fraction, is about something 0.84, and then you need to substitute into this equation to find parameter A. To find parameter B, again you have to substitute F, ultimate strength, and endurance strength. Okay, look at this equation. In this equation, SF stands for fatigue strength and N stands for number of cycles. In one case, maybe you want to find how much is the fatigue strength under a specific number of rotation or number of cycle. That means the number of cycle is known and you want to know how much load or how much stress you can expose to the load. Or in some other case, maybe the strength is known and you want to find the number of cycles. If you substitute SE, if you substitute SE here, okay, then here you will find 10 power 6. That means for 1 million cycle, the fatigue strength is equal to endurance strength. Or if you, in another word, if you apply a stress equal to endurance strength, you will get 10 million cycle life. Maybe to elaborate this, we solve this example together. Here we have a rotating beam. Okay, so the rotating beam is made from this material. Okay, 1050 hot rolled steel. Then you are required to find the rotating beam endurance limit at 10 power 6 cycle. The rotating beam. What's the rotating beam? When rotating beam means exactly that sample we are using in the lab. This is rotating beam. We are talking about this. So you are required to find endurance strength of this rotating beam under lab condition. And as I told you, one of the method to approximate this endurance strength is to find 50% of ultimate strength of the material. This material, its ultimate strength is 630 kpsi and 50% of this value is 350 megapascal. Sorry, this is I think that this is megapascal. Sorry. Okay. The endurance, you have to find the endurance strength of the polished rotating beam specimen corresponding to 10 power 6 cycle. We have to find SF, okay, we have to find SF for n equal to 10 power 4 cycle. We want to find this. That means the cycle is given. Then we want to find SF. First, for this, you have to refer to the metric version of this graph. Okay, use the metric version of this graph to find F for 630 megapascal, which is 86, which is 0.86. Then you can substitute to this equation to find parameter A or constant A and to find parameter or constant B. Okay, so we will find these two constants. Then we will substitute to this equation. That means here, okay, A should be substitute here, B is a power of n, and then as I told you, the number of cycle was given, which is 10 power 4. Then you will find this fatigue strength. That means if you apply this stress on the rotating beam under lab condition, the life will be 10 power 6. So as you can see, how much was the endurance strength of the material? Endurance strength of material was, we approximate here 350, right? 350. If you want to find the safety factor, fatigue safety factor of this case is 315 over 526, which is less than 1. Then the number of cycle is less than 10 power 6 because n was 10 power 4, right? That means if you substitute 350 here, you will get 10 power 6. How much is the how much is the expected life of a polished rotating beam specimen? That means again it's referring to a specimen under lab condition, polished rotating beam specimen. Until now, we are not talking about the actual part in application. We are talking about the lab specimen under complete reverse stress of 385 megapascal. That means sigma max, let me write in part C. That means sigma max is 385 megapascal. How much is safety factor in this case? Our endurance strength of material was 350, right? 350 over sigma max, which is 385. So it is less than 1. Then n is less than 10 power 6. Now I want to find out how much is n. Okay, first of all, let me tell you something. That you are allowed to use this equation. You can use this equation only for the case that safety factor is less than 1. For this case, when the life is finite, this equation is not valid for safety factor greater than 1. This equation is not able to predict the number of cycles for infinite life. So you are not allowed to use this equation under this condition. And one more thing that you have to notice, this equation is valid when the load is completely reversed. You are not able or you are not allowed to use this equation for fluctuating stress. Fluctuating stress means sigma max is not equal to absolute value of the sigma mean. So I will repeat one more time that this equation is only valid for finite life and for the case that load is completely reversed. Sigma max equals to absolute value of the sigma mean, and you are not allowed to use it for fluctuating load. Okay, so because the safety factor become less than 1, the fatigue safety factor become less than 1, and we have complete reverse stress, because here mentioned complete reverse stress. So I'm able to use the equation to predict the number of cycles. So if you solve this equation, where is the equation that we have here? If you solve this equation to find n, then you can use this. It's same, it's exactly this, but we write it in this way to find, or we solve it for n. Sigma reverse, or maximum value of the reverse complete stress, divided by a power 1 over b. Okay. So how much was the maximum value? 385 divided by the value of a, or constant a, which we found earlier, 1084, power 1 over b, which was equal to this. So the number of cycle, right, it would be 53.3 10 power 6, which is less than 1 million cycle. It is less than 10 power 6. Okay, so thank you. I think it's end of this topic, and thank you very much for your attention.